Today's hybrid electric vehicles, HEVs, are powered by an internal combustion engine in combination with one or more electric motors that use energy stored in batteries. HEVs combine the benefits of high fuel economy and low tailpipe emissions with the power and range of conventional vehicles. Hybrid electric vehicles are powered by an internal combustion engine and one or more electric motors, which uses energy stored in batteries. A hybrid electric vehicle cannot be plugged in to charge the battery. Instead, the battery is charged through regenerative braking and by the internal combustion engine. The extra power provided by the electric motor can potentially allow for a smaller engine. The battery can also power auxiliary loads and reduce engine idling when stopped. Together, these features result in better fuel economy without sacrificing performance. A wide variety of HEV models are currently available. Although HEVs are often more expensive than similar conventional vehicles, some cost may be recovered through fuel savings or state incentives. Compare HEV and non-hybrid models side by side using the Can a Hybrid Save Me Money tool on fueleconomy.gov. The tool compares the costs of a selected HEV with a comparably equipped non-hybrid model from the same manufacturer and provides fuel cost savings associated with the HEV option. In an HEV, the extra power provided by the electric motor may allow for a smaller combustion engine. The battery can also power auxiliary loads and reduce engine idling when the vehicle is stopped. Together, these features result in better fuel economy without sacrificing performance. An HEV cannot plug into off-board sources of electricity to charge the battery. Instead, the vehicle uses regenerative braking and the internal combustion engine to charge. The vehicle captures energy normally lost during braking by using the electric motor as a generator and storing the captured energy in the battery. HEVs can be either mild or full hybrids, and full hybrids can be designed in series or parallel configurations. Mild hybrids, also called micro-hybrids, use a battery and electric motor to help power the vehicle and can allow the engine to shut off when the vehicle stops, such as at traffic lights or in stop-and-go traffic, further improving fuel economy. Mild hybrid systems cannot power the vehicle using electricity alone. These vehicles generally cost less than full hybrids but provide less fuel economy benefit than full hybrids. Full hybrids have larger batteries and more powerful electric motors, which can power the vehicle for short distances and at low speeds. These vehicles cost more than mild hybrids but provide better fuel economy benefits. There are different ways to combine the power from the electric motor and the engine. Parallel hybrids, the most common HEV design, connect the engine and the electric motor to the wheels through mechanical coupling. Both the electric motor and the internal combustion engine drive the wheels directly. Series hybrids, which use only the electric motor to drive the wheels, are more commonly found in plug-in hybrid electric vehicles. A hybrid vehicle is one that uses two or more distinct types of power, such as submarines that use diesel when surfaced and batteries when submerged. Other means to store energy include pressurized fluid in hydraulic hybrids. Hybrid powertrains are designed to switch from one power source to another to maximize both fuel efficiency and energy efficiency. In hybrid electric vehicles, for instance, the electric motor is more efficient at producing torque, or turning power, while the combustion engine is better for maintaining high speed. Improved efficiency, lower emissions, and reduced running costs relative to non-hybrid vehicles are three primary benefits of hybridization. Mopeds, electric bicycles, and even electric kick scooters are a simple form of a hybrid, powered by an internal combustion engine or electric motor and the rider's muscles. Early prototype motorcycles in the late 19th century used the same principle. In a parallel hybrid bicycle, human and motor torques are mechanically coupled at the pedal or one of the wheels, e.g. using a hub motor, a roller pressing onto a tire, or a connection to a wheel using a transmission element. Most motorized bicycles, mopeds, are of this type. In a series hybrid bicycle, SHB, a kind of chainless bicycle, the user pedals a generator, charging a battery or feeding the motor, which delivers all of the torque required. They are commercially available, being simple in theory and manufacturing. The first published prototype of an SHB is by Augustus Kinzel, U.S. Patent 3884317, in 1975. In 1994 Bernie McDonald's conceived the Electrolite SHB with power electronics allowing regenerative braking and pedaling while stationary. In 1995 Thomas Muller designed and built a Farad MIT electromagnetischem Antrieb for his 1995 diploma thesis. In 1996 Georg Blatter and Andreas Fuchs of Bern University of Applied Sciences built an SHB and in 1998 modified a Litra tricycle, European patent EP1165188. Until 2005 they built several prototype SH tricycles and quadricycles. In 1999 Harold Kutsky described an active bicycle. The aim is to approach the ideal bicycle weighing nothing and having no drag by electronic compensation. A series hybrid electric petroleum bicycle, SHEP, is powered by pedals, batteries, a petrol generator, or plug-in charger providing flexibility and range enhancements over electric-only bicycles. A SHEP prototype made by David Kitson in Australia in 2014 used a lightweight brushless DC electric motor from an aerial drone and small hand tool-sized internal combustion engine, and a 3D printed drive system and lightweight housing, altogether weighing less than 4.5 kilograms. Active cooling keeps plastic parts from softening. The prototype uses a regular electric bicycle charge port. Hybrid powertrains use diesel-electric or turbo-electric to power railway locomotives, buses, heavy goods vehicles, mobile hydraulic machinery, and ships. A diesel/turbine engine drives an electric generator or hydraulic pump, which powers electric/hydraulic motors. Strictly an electric/hydraulic transmission, not a hybrid, unless it can accept power from outside. With large vehicles, conversion losses decrease and the advantages in distributing power through wires or pipes rather than mechanical elements become more prominent, especially when powering multiple drives, e.g. driven wheels or propellers. Until recently most heavy vehicles had little secondary energy storage, e.g. batteries/hydraulic accumulators excepting non-nuclear submarines, one of the oldest production hybrids, running on diesel while surfaced and batteries when submerged. Both series and parallel setups were used in World War II-era submarines. The new Autorail à grande capacité, AGC or high-capacity railcar, built by the Canadian company Bombardier for service in France is diesel/electric motors, using 1,500 or 25,000 V on different rail systems. It was tested in Rotterdam, the Netherlands with Rail Feeding, a Genesee and Wyoming company. The first hybrid evaluating locomotive was designed by Rail Research Centre Matre in 1999 and built in 2000. It was an EMDG-12 locomotive upgraded with batteries, a 200 kW diesel generator, and 4 AC motors. Japan's first hybrid train with significant energy storage is the Kihei 200, with roof-mounted lithium-ion batteries. Indian Railway launched one of its kind CNG diesel hybrid trains in January 2015. The train has a 1,400 HP engine which uses fumigation technology. The first of these trains is set to run on the 81 km long Rewariro-Rohtak route. CNG is less polluting alternative for diesel and petrol and is popular as an alternative fuel in India. Already many transport vehicles such as auto rickshaws and buses run on CNG fuel. In the US, General Electric made a locomotive with sodium, nickel chloride, NaNiCl2, battery storage. They expect greater than or equal to 10% fuel economy. Variant diesel-electric locomotive include the Green Goat, GG, and Green Kid, GK, switching/yard engines built by Canada's Rail Power Technologies, with lead-acid, PBA, batteries and 1,000 to 2,000 HP electric motors, and a new clean-burning 160 HP diesel generator. No fuel is wasted for idling, 60–85% of the time for these types of locomotives. It is unclear if regenerative braking is used, but in principle, it is easily utilized. Since these engines typically need extra weight for traction purposes anyway, the battery pack's weight is a negligible penalty. The diesel generator and batteries are normally built on an existing retired yard locomotive's frame. The existing motors and running gear are all rebuilt and reused. Fuel savings of 40 to 60% and up to 80% pollution reductions are claimed over a typical older switching/yard engine. The advantages hybrid cars have for frequent starts and stops and idle periods apply to typical switching yard use. Green Goat locomotives have been purchased by Canadian Pacific, BNSF, Kansas City Southern Railway and Union Pacific among others. Rail Power Technologies engineers working with TSI Terminal Systems are testing a hybrid diesel-electric power unit with battery storage for use in rubber-tired gantry, RTG, cranes. RTG cranes are typically used for loading and unloading shipping containers onto trains or trucks in ports and container storage yards. The energy used to lift the containers can be partially regained when they are lowered. Diesel fuel and emission reductions of 50 to 70% are predicted by rail power engineers. First systems are expected to be operational in 2007. Hybrid systems are regularly in use for trucks, buses, and other heavy highway vehicles. Small fleet sizes and installation costs are compensated by fuel savings, with advances such as higher capacity, lowered battery cost, etc. Toyota, Ford, GM, and others are introducing hybrid pickups and SUVs. Kenworth Truck Company recently introduced the Kenworth T270 Class 6 that for city usage seems to be competitive. FedEx and others are investing in hybrid delivery vehicles, particularly for city use where hybrid technology may pay off first. As of December 2013, FedEx is trialing 2 delivery trucks with Wright-speed electric motors and diesel generators. The retrofit kits are claimed to pay for themselves in a few years. The diesel engines run at a constant RPM for peak efficiency. In 1978, students at Minneapolis, Minnesota's Hennepin Vocational Technical Center, converted a Volkswagen Beetle to a petro-hydraulic hybrid with off-the-shelf components. A car rated at 32 mpg was returning 75 mpg with the 60 HP engine replaced by a 16 HP engine, and reached 70 miles per hour. In the 1990s, engineers at EPA's National Vehicle and Fuel Emissions Laboratory developed a petro-hydraulic powertrain for a typical American sedan car. The test car achieved over 80 mpg on combined EPA city/highway driving cycles. Acceleration was 0 to 60 miles per hour in 8 seconds, using a 1.9-liter diesel engine. No lightweight materials were used. The EPA estimated that produced in high volumes the hydraulic components would add only $700 to the cost. Under EPA testing, a hydraulic hybrid Ford Expedition returned 32 mpg, 7.4 L/100 km, city, and 22 mpg, 11 L/100 km, highway. UPS currently has 2 trucks in service using this technology. Since 1985, the U.S. military has been testing serial hybrid Humvees and have found them to deliver faster acceleration, a stealth mode with low thermal signature, near-silent operation, and greater fuel economy. Ships with both mast-mounted sails and steam engines were an early form of a hybrid vehicle. Another example is the diesel-electric submarine. This runs on batteries when submerged, and the batteries can be recharged by the diesel engine when the craft is on the surface. As of 2022, there are 550 ships with an average of 1.6 MWh of batteries. The average was 500 kWh in 2016. Newer hybrid ship propulsion schemes include large towing kites manufactured by companies such as Skysails. Towing kites can fly at heights several times higher than the tallest ship masts, capturing stronger and steadier winds. The Boeing Fuel Cell Demonstrator airplane has a proton exchange membrane, PEM, fuel cell/lithium-ion battery hybrid system to power an electric motor, which is coupled to a conventional propeller. The fuel cell provides all power for the cruise phase of flight. During takeoff and climb, the flight segment that requires the most power, the system draws on lightweight lithium-ion batteries. The demonstrator aircraft is a Dimona motor glider, built by Diamond Aircraft Industries of Austria, which also carried out structural modifications to the aircraft. With a wingspan of 16.3 meters, 53 feet, the airplane will be able to cruise at about 100 kilometers per hour, 62 miles per hour on power from the fuel cell. Hybrid fan wings have been designed. A fan wing is created by two engines with the capability to auto-rotate and landing like a helicopter. There is an impending increase in the costs of many rare materials used in the manufacture of hybrid cars. For example, the rare earth element dysprosium is required to fabricate many of the advanced electric motors and battery systems in hybrid propulsion systems. Neodymium is another rare earth metal which is a crucial ingredient in high-strength magnets that are found in permanent magnet electric motors. Nearly all the rare earth elements in the world come from China, and many analysts believe that an overall increase in Chinese electronics manufacturing will consume this entire supply by 2012. In addition, export quotas on Chinese rare earth elements have resulted in an unknown amount of supply. A few non-Chinese sources such as the advanced Hoytas Lake project in northern Canada as well as Mount Weld in Australia are currently under development. However, the barriers to entry are high and require years to go online. Other types of green vehicles include other vehicles that go fully or partly on alternative energy sources than fossil fuel. Another option is to use alternative fuel composition, i.e. biofuels, in conventional fossil fuel-based vehicles, making them go partly on renewable energy sources. Other approaches include personal rapid transit, a public transportation concept that offers automated on-demand non-stop transportation, on a network of specially built GUIDAVs. What type are you driving by now? Thank you for watching this video.